Hello, this video is the second part of my principal components analysis walkthrough. Here I cover additional types of the output. In particular, I visualize extreme points of first three principal components and compare them to the average structure of my index group, which I used in analysis. Also, I visualize the filtered trajectory where all the conformational motion is restricted to first three principal components. However, in this video I did not cover the comparison of principal components from different trajectories. This type of analysis can be particularly useful when you want to determine how substitutions of amino acid residues in two evolutionary related proteins impacted the conformational motion. So I will probably make another video on this topic in the future when I will have two proper structures to compare. Now let's get back to the subject of this video. As you have noticed, I reran the anaeig tool and I have changed two output files. Particularly, I have added PDB files with extreme points of each principal component, and I have also changed the format of the filtered trajectory output. Previously it was PDB file with multiple models, now it is a compressed GROMACS trajectory file. I didn't clean the previous output because I want GROMACS to back it up so that new files are clearly visible. As in the previous video, we have the same index group with backbone atoms, among which only those that belong to disordered regions are movable and the rest of them are immovable inside of the global. As you can see, for each of the three principal components, anaeig tool has identified the extreme points, namely the point of minimum and the point of maximum expansion. All the previously existing files with name matching names in the output of the current run of the anaeig tool were backed up, except for the filtered PDB file, because the new file with filtered trajectory was written in XTC format. Let's visualize the extreme points of each of the three principal components using ChimeraX. Here I restricted visible models only to the average structure and extreme points of the first principal component. I have colored the average structure in blue, the point of maximum expansion in red, and the point of minimal expansion in green. Based on this alignment, we can see that atoms in loop disordered regions have the largest variability of their positions. Inside of the globular, almost no motion occurs. Thus, we can explain the high cosine content observed in the previous part of the PCA walkthrough by the fact that the most of the atoms are located inside of the globular and there is almost no variability in their positions. Now let's visualize our filtered trajectory using VMD tool. It is important to remember that this trajectory does not contain actual conformations obtained during molecular dynamic sampling, but rather it is the projection of those conformations onto the first three principal components. In other words, such trajectory contains essential dynamics of our system. Here I configure molecular representation so that conformational changes were clearly visible.